Good morning, everybody. So we'll start the morning session with Nima Arkani Hamed from the IAS, talking about positive geometry. And the... Do you want to do the...
No, I'm fine, yeah. Thanks. All right, guys, it's really wonderful to be here. I faced a comic series of terrible incidents yesterday that stopped me from getting here as I wanted to yesterday. And lucky for you, I'm about to give a normal length talk for the first time in my life because I have to leave at 10:35 okay? To get back on, after arriving at 5 a.m., to get back on a flight to go back to the States for things that I cannot avoid on the other end. But come hell or high water, I was going to come here, and part of the reason I wanted to come, first, it's an honor to be invited, as always, and secondly, it's the 10th, it's 10 years since I came to my first Amplitudes conference, and anyway, I'm really delighted to be here. I'm starting with the picture that I've started with for almost all of these 10 years, some version of this picture. The moving question is, what question should we be asking to which the scattering amplitudes are the answer, other than just local evolution and local unitary evolution in space-time. And for 10 years, but quite a bit more intensely over the last 2 years, where we finally started asking this question directly in the space where the scattering amplitudes live, directly in kinematic space, we're starting to see that at least some aspect of the answer to these questions involves surprising ideas in combinatorics, positive geometry, and related things directly in kinematic space. And the first thing I want to do, to those of you who have not been paying any attention to these things for all this time, is give a different invitation to the subject. I want to imagine that you're some kind of experimentalist who lives at infinity, who has their fingers on the Mandelstam dial. You have to be a little generous here. A finger on the Mandelstam dial means that you're allowed to dial up all possible real values of the Mandelstam invariant. It's not possible in Minkowski space, but it's possible in 2-2 signature. Anyway, never mind. Anyway, they have the fingers on the Mandelstam dial, and they're moving the Mandelstams around, and they notice features of this mysterious thing that's going on the inside. And they're going to report these results at the Morillon meeting in this imaginary universe. And now I want to talk about what two kinds of experimentalists see. Experimentalist number one is who I call a closet theorist. Some experimentalists really would have rather been theorists. And so this experimentalist notices that the amplitudes blow up somewhere. They blow up when the sum of the subset of momenta go to 0. And because they're closet theorists, they care about poles and residues, so they're going to go measure what the residue looks like on the pole. And of course, they notice the magic that on the pole, the amplitude factorizes into the product of two smaller pieces. So, aha, they say that's the clue to what's going on. They announce it Morillon, the imaginary world. And there are two theorists in the audience who say, from that clue, I know what's going on. Theorist number one is named Feynman and says, aha, what's really going on is really I'm summing over diagrams like this with virtual particles on the inside, and when the virtual particles go on shell, that's locality, and they factorize on the poles manifestly. Theorist number two is named Deline and Mumford and friends, and they say, aha, I've seen this before. The dumbest first moduli space you've ever seen in your life in mathematics is endpoints on P1. The moduli space of endpoints on P1 has this exactly the same factorization structure on the boundary, so that must be what's going on, and that's associated with the picture of the string worldsheet. So factorization is the star of the show. There are two basic pictures in the last 50 years of thinking about scattering amplitudes that go along with them, particles in space-time or the string worldsheet. And you might think there's nothing more to be desired. That's what you would think because you're a theorist. But there's the second kind of experimentalist, the hero of this story, is not a closet theorist, doesn't give a shit about theory, and they're lazier but smarter. And they don't care about poles or residues, they don't know anything crap like that. All they notice is the amplitude blows up somewhere, and then what do they want to do? They move the other Mandelstams around to make it blow up more. And then moves around, also make it blow up even more. So they noticed a pattern in the sets of poles that are allowed to come together. 1 pole, 2 pole, 3 poles. And they notice for n equals 4, you can have S and T, but not both S and T. For n equals 5, you can have S12 and S123, and the cyclic friends of them imagining what's really secretly going on is the sum of planar tree diagrams, just for this example, but not the other combinations. And they're good experimentals, so they even show how to represent this data, this qualitative combinatorial data as a graph. So they say, here's the n equals 4 amplitude, but these are the two kinds of poles that it can have, S and T channel poles. Here's an n equals 5. Here's the first single kind of pole that it can have. But interestingly, you can represent the sort of way that the poles are related to each other by a graph that looks like a pentagon, where you can further go to the double poles from the single pole by further blowing up one of the vertices on this side. And they can keep going, and if they have a lot of imagination, they can actually notice that that keeps going to 6 points. This is much less obvious. In the real world, not the imaginary world, this is what took Jim Stashev to do in the 1960s to realize that triangulations, or to realize that these cubic graphs can actually be thought of as vertices of a polyhedron. And it actually was not 20 years until after Stashev till people really figured out how to cut these objects out as polytopes with flat faces. Even when Stashev did in the 1960s, it was purely a topological statement. But this is the combinatorial isosahedron. And again, two vertices here are connected by a line if there's a coarser factorization that contains the finer factorization channels in them. And what I want to stress is that this is a remarkable fact about the pattern of poles that the answer has. This fact is not obvious in the particle picture. It's not obvious in the string picture. It's yet another fact, qualitative simple fact about the amplitudes, which Feynman doesn't know and Deligne doesn't know. But this isosahedron knows, and it not only knows that, it also knows about Feynman, it knows about factorization, because this polytope has a remarkable property that its boundaries factorize into the product of lower polytopes of the same sort. For example, in this case, you see there are these pentagonal faces that correspond to the 5-3 factorization channels, and the square faces that look like an interval times an interval that correspond to the 4-4 factorization channels. So this is another invitation to this subject. It's another invitation. There's something qualitative and simple about the structure of amplitudes, which begs for something more deeply combinatorial, something that's not in all of our textbooks, but more that's going on, and which actually contains the things that are in the textbooks as a special case, right? So now the question is, how can we make this obvious? And the idea is that making this obvious should be a qualitative clue to whatever this theory is that we're looking for in kinematical space. Now, a couple of years ago, some of us found a very specific realization of the isosahedron, not just the combinatorial isosahedron, but a very specific one in work with Song, Yuntao Bai, and Gongwan Wan, ABHY. So this is a specific realization of the isosahedron, not one of the ones that had been written down by mathematicians before. Relatively quickly after us, Hugh Thomas and his students realized that this construction of the isosahedron actually generalized to a larger set of polytopes associated with combinatorial objects that go along with cluster algebras. So there's a whole collection of polytopes associated with cluster algebras, and they all have these ABHY type realizations. And in fact, gives a sort of conceptual explanation to some extent of where these polytopes come from. So that's one step to making this obvious. These polytopes live in kinematic space, so they live in the space of the Mandelstam, in this case the planar Mandelstams conveniently given by these x variables. So this is a step in the direction of making this obvious, but now we still like to know where the heck does ABHY come from? Okay, why do we make this particular choice to cut out the polytope in this way? All right, so those are the things that I want to talk about today, and actually over the past year, so some of these things we talked about at Amplitude last year, and a lot of our work of my friends and I over the past year has been pursuing this question. How do we make this obvious? And pursuing this question over the last year has led to, at least to me, a kind of a mind-boggling, striking convergence of a large number of separate lines of research. So there's positive geometries in Grassmannians and amplituhedra, cluster algebras and polytopes, string amplitudes, CHY and scattering equations, and n equals 4 amplitudes in cluster symbology. All are sort of colliding together on one underlying set of ideas, together with generalizations of open and closed string particle amplitudes, as well as some practically useful and interesting new links to arithmetic geometry that I probably won't have any time to talk about today. But this is an outline of things that I will try to say something about. It's a little bit insane to try to say something about all of them, but I'll try to say something about all of them, partially because they're all so closely interconnected to each other that it's very difficult to peel pieces apart and talk about them in isolation. So I'll first talk about the underlying simple model. There's some underlying simple 1 plus 1 dimensional structure that seems to be related to many of these things, and that has everything to do with causal diamonds, and associated with that, the picture of cluster polytopes. So this is going to be the ABCDs of the biadjoint phi cube theory through to one loop. So one concrete thing that you're going to see are amplitahedra for the biadjoint phi cube theory through to one loop. I'll say one slide on an all loop, what we know about these things at all loops, and there's a certain hidden symmetry, even of dumb-old phi cube theory, that appears to be true at all loop order, even though we're still searching to find the underlying geometry. Then I'll move on to the subjects in purple I will spend a little bit more time talking about. I'll then move on to talk about the very simple but important notion of stringy canonical forms, which give a conceptual and simple understanding of scattering equations and of the idea of scattering equations in total generality. Okay, so there's a very large set of objects for which the correspondence between stringy objects that as alpha prime goes to infinity are controlled by Gross-Mendel-like scattering equations that mysteriously produce the answers for what you would expect as alpha prime goes to 0, that correspondence has nothing to do with strings. It's something totally general for essentially any polytope. And it's associated with the notion of a stringy canonical form, which I will define and talk about. Then I'll say a little bit about binary positive cluster geometries, what we call U-space, and the notion of different orderings. So this is something that's this is a new part of the geometry of cluster algebras and cluster varieties, which is not standard in the world of the cluster algebraists, but is really forced on us in this way of thinking about things. Then I'll talk about this generalization of particle and string amplitudes. It really begins life naturally as a generalization of string amplitude. So there's going to be a generalization of the notion of string amplitude associated with any cluster algebra. Okay? And these are going to be objects that have all the same miraculous properties that we normally ascribe to string amplitude, but there's no seeming underlying world sheet. It's just something different. I'll say nothing about the arithmetic geometry that goes along with this, other than to tell you that it's extremely practically useful and interesting. And finally, I will say something, and all these things are related, I'll say something about thinking about the positive Grassmannian modulo the little group, modulo the torus, its connection with a particular case of G4n mod torus, and its relation to n equals 4 super Yang-Mills symbology. All right, so let's get going. Just to say two of the things one thing I'll talk very little about, the other one that I'll say a little about, and this is a little bit more for the cluster experts in the audience. There is something lurking in all this cluster business, which is a certain infinity that shows up in cluster algebras very, very quickly. A lot of the story is going to be about finite type, but in these two cases, we have to encounter the infinity in an interesting way, and there are ways of taming this infinity in both these cases that I want to that I'll be saying something a little bit about. All right, so let's first get into the first subject, causal diamonds, cluster polytopes, and biadjoint amplitudes. This is work with Song, Hugh Thomas, and Giulio Salvatore, who's here. All right, so forget about everything. We're going to go all the way back to thinking about the wave equation in 1 plus 1 dimensions. All right, so here's the wave equation in 1 plus 1 dimensions, time and space, the light cone variables u and v. All right, so here it is, the wave equation with a source little j. The Gauss law for the wave equation in 1 plus 1 dimension is especially simple for causal diamonds. So if you give me a causal diamond here, and the values of x at the corners are a, b, c, d, then Gauss's law just tells you that a plus b minus c minus d is equal to the total current through that diamond. All right? And there's another simple rule about the wave equation in 1 plus 1 dimensions that we'll need. Let's say you have a solution to the wave equation that has a 45-degree strip here, and some solution x right out here and x left down here. Then you see, because of this Gauss's law rule, and obviously if you take this Gauss law and you scrunch the diamond to 0 size, you recover the wave equation. So the Gauss's law, the sort of most fundamental thing there is here, well, this Gauss's law immediately tells you that from this solution, you can build another solution where you just scrunch away this region. You leave it as x right and x left out there, but the effect of any source that was there has got to be added as a delta function source at that juncture. Okay, so these are two basic facts about the wave equation in 1 plus 1 dimensions. Now, we're going to add the magic word positivity. which is something that happens over and over again in this business, or we're now going to ask for something positive about the wave equation in 1 + 1 dimensions. I'm going to imagine that I have a causal diamond, except just this little half of a diamond. So on these 45-degree lines, I can imagine giving initial conditions A at U, B at V. I'm going to ask that at the tip x equals 0, and the basic question I want to ask is, if the source is positive, what boundary conditions can I impose on A at U and B at V to force the solution X to be positive everywhere inside? Okay, so that's all we're doing. We ask the source to be positive and the solution to be positive everywhere inside. A little bit of thought shows that to solve this problem, it suffices to solve the problem where you also force X to be 0 at the top. So those are the boundary, and then from there you can get the general case. I won't talk about it. So we're going to restrict ourselves to looking at the problem where X is 0 at the top. It's 0 at the bottom here. The source is positive. Sorry, that was supposed to be little j. Sorry, I switched the notation. And so now, in the world of the boundary conditions A at U and B at V, we want to know what boundary values A at U and B at V are compatible with these things. Obviously, they have to be positive, but what else has to be the case? All right, well, that problem is too hard, so let's start investigating what happens if I just sample the value of A at a few points. So let's just begin with 1 point, and actually already we learned something interesting, that A and B are not independent of each other, because if I look at this little Gauss's law for this diamond, I get that A1 plus B1 minus 0 is equal to J. Okay, so B is a slave to A, or the other way around, so the data that I'm interested in lives just in the space of A's, let's say, the boundary values on one end. Okay, but now we also learned something, that A has got to live between this this region from 0 to J. Obviously, it's got to be positive, but also can't be bigger than J, because when it is bigger than J, B becomes less than 0. So that's what happens when I'm just sampling at 1 point. The possible values of A have to live in an interval. Let's move on to 2 points. So let's look at A1 and A2 here. Okay, and now I draw the obvious light rays in this picture. So I have these points B1 and B2 and C there. And now you see I have a total of 5 variables, but I have 3 of these Gauss's law relations, or what we call mesh relations. So A1 plus C minus A2 is whatever that source is. C plus B2 minus B1 is whatever that source is. A2 plus B1 minus C is whatever that source is. So there are 3 equations, 5 unknowns. I can solve for 3 of them in terms of the 2. And now I'm going to just ask again, in the space of A1, A2, what's the allowed region in A1 and A2 which keeps positivity everywhere? And you can work out the answer is the inside of a little pentagon. It's already pretty cool that a pentagon comes out of this little question. Of course, you see where this is going. If we now ask at 3 points, now I draw the light rays in this picture. Now there are 3 values here. There are a total of 9 variables, 6 mesh relations. I've written them all down. I again ask for everything to be positive, and you exactly get the ABHY isosahedron. So this is the ABHY isosahedron. The ABHY isosahedron is simply positivity of the wave equation in 1 + 1 dimensions. Okay. Now, why does that happen? This is not an accident. And it's because the boundary structure of the space is trivial to figure out. This is an extremely simple and beautiful thing. What is the boundary? How do I go to a boundary here? The boundary means that even though X is forced to be, in general, greater than or equal to 0, on the inside, going to a boundary means that somewhere you set X equals 0. So let's say I'm going to stick X equals 0 here at that point. Okay? Having put X equals 0 there, we can now naturally ask, where else can I put X to 0? And now you see there's a very pretty thing. I cannot put X to 0 anything in this shaded region. Anywhere which is space-like separated, but causally disconnected, but causally connected to X, I cannot set X to 0. Why? Because if I can manage to draw a little diamond that fits inside this space-time here, then if this is X at one corner, I can't put another corner to 0, because I have the Gauss's law that says this plus this minus that is the source. Remember, everything is positive, so I'm setting these things to 0. I have the sum of 2 negative things equaling a positive thing, and that is impossible. Right? So, okay, so I can't set anything to 0 in here, but it's actually more interesting than that. So I can't set anything to 0 in there, and furthermore, I can totally reconstruct everything that happens inside here from knowledge of things on the boundaries, sort of trivially by causality. And so that means that for the purpose of knowing what the boundary structure looks like, the inside there is totally irrelevant. In fact, I can make a new solution to the wave equation just by scrunching away that region and that region. So there it is. I scrunch that triangle down there. I scrunch that triangle down there. I replace this source with some positive delta function source here, that by some positive delta function source there. And now what do I see? I see that on this boundary, I get nothing other than the factorization into two triangles. Exactly the same problem. So factorization is obvious in this picture. I find this totally remarkable because finally there's a picture, unlike the particle and string pictures, where the polytopic property is manifest, it's just built in, and factorization is obvious. Everything is obvious from this picture now, finally. Okay. All right, in fact, you can motivate this entire picture just by thinking about what labels you should give these xij's. So these xij's have labels of the diagonals of a polygon. If you just try to label the diagonals of a polygon, you have this little problem that ij and ji are the same. So if you're just going to label them 1, 2, 2, 3, 3, 4, 4, 5, I'm going to label them on a grid in this way. Then you see, if you sort of take a continuum limit of this picture, then if the height in the time direction is 1, it has to have a periodicity 2 in the space direction, and it has to have this interesting Mobius identification where ij goes to ji identifies xt with 1 plus x and 1 minus t. Okay, so this is purely the representation of the indices that correspond to the diagonals of a polygon. But what correspond to this causal relationship inside this strip between A and B under this identification is precisely whether the corresponding chords of the xij's intersect or not. So we see that the 1 plus 1 dimensional causal structure of this wave equation model implies factorization via this simple identification of the indices of the xij with the points on the grid in this 1 plus 1 dimensional space-time. In fact, once you make this realization, you can do much more general things. The general story is that is that you can choose any time-like curve here, another time-like curve on the other side, which is what you get by translating it forward in x by 1 and flipping it over, so c and its conjugate, and any region of area 1 in here contains one of the xij's once and only once. Okay, so all you need to do is cut out of this region something that picks all the ij's out once and only once, and any way of doing that you then further discretize and it gives you an icosahedron. Okay, so for instance, something you can do is make a square shape, and in total generality you can again go through the factorization arguments and the scrunching and see the things that factorize. Now, one general comment is that the fact that there's a polytope here makes projective invariance of canonical forms manifest. What that means is that the amplitude, as has been the case in this business for a long time, I won't review, the amplitude is actually associated with a differential form that has logarithmic singularities on all the facets of these geometries. And in particular, these forms have no pole at infinity. And that means that they have an invariance under rescaling xij by any function of x times xij. They're only functions of ratios of these x's. Strikingly, Feynman diagrams do not make this fact obvious. Every diagram, piece by piece, does not have this property. And Feynman diagrams are a particular triangulation of the icosahedron involving some auxiliary plane at infinity, which breaks this projective invariance, term by term. Only the sum of all of them has it. Projective invariance is to phi cubed bi-adjoint theories as dual conformal symmetry is tan equals 4 super Yang-Mills. They're very spiritually connected to each other. And it's a hidden symmetry of even this stupid old phi cubed theory. It's something we already emphasized at amplitudes last year. But now that we have this more physical picture of the origin of the icosahedron, there's all kinds of properties of the ABHY icosahedron that we had not noticed before that become totally obvious in this picture. Which are related to projectivity, give rise to just new formulas, new recursion relations for these phi cubed amplitudes. They're not BCFW, they're not any of the recursion relations that we knew before. They're new, extremely efficient recursion relations for even these stupid old scalar theories. And there's a number of ideas, but one of them is very simple. You see, I wanted to know what was going on at all these points. Well, what if I just want to forget about this one? Forget about this middle point. In the geometry, I'd literally project through that guy. Well, it turns out that if you project through that guy, it's really as if you just eliminated that light ray. And you go from this geometry to that one, and the n+1 icosahedron literally one-dimensionally fibers over AN. Okay, so I won't go through this in any detail, but you can see it's sort of trivial in the case of the pentagon, that if you look at the pentagon from any one of these directions, of course it collapses to an interval. It's a little more interesting for the three-dimensional icosahedron, where if you look at that picture from any direction, you see that it collapses to a pentagon. And for some of them it's obvious, and some of them it's not so obvious. That fact that the amplitude, that the icosahedron has a one-dimensional fiber that lifts, so it really is kind of unfolds like an accordion. As you go to higher and higher points, you have the old geometry, and you just add one dimension to it, and it gets bigger. And if you forget about that direction, it just projects right back down to the guy that you had before. That gives rise to a recursive formula for the amplitude. Here is the expression. I've just written it down for the case of 5 points, just so you see. It doesn't look like the usual ones. It only is a sum of 2 terms. In general, it's a sum of n minus 3 terms. Of course, each term gets longer and longer on the inside, but it's built recursively. And that's just to show that it looks absolutely nothing like Feynman diagrams, not even close. It's a sum of n minus 3 terms, and just practically speaking, it is efficient. Again, this is related both to this interesting geometry of the icosahedron, this forgetting, not forgetting feature that's made obvious in the wave equation picture, and somewhat more fundamentally to this projective invariance. All right, so now, having seen that we can understand from these pictures of causality in 1+1 dimensions, the origin of locality and of factorization, so factorization for tree amplitude says that we have something like the poles of A factorized into 2 A's, and we know that comes from trees. Well, there's a few other things that we can look at. We can look at things that look like one-loop diagrams just emitting tadpoles. This might seem a little funny to focus on diagrams like this, but in the context of string theory, for example, this is very natural to be thought of as sort of zero momentum dilaton emission at the same time. So sort of emitting tadpoles is a reasonably interesting thing. And then finally, we can go to one-loop amplitudes. And purely at the level of pictures and factorization, these involve just slight modifications of this basic picture of factorization. Okay, so instead of an A going to an A and an A, here we have a B that can factorize into a B and an A, because the tadpole is always going to be on one side of the diagram, or a D that can go to a D and an A, as well as the sort of forward limit piece of an A itself. And all of these things can actually arise also from 1+1 dimensional meshes. And I've shown you examples here. In fact, to get the B and C, the C type, the tadpole mesh, you literally start with a realization of AN in the way I showed you now, in a way that looks like a square rather than a triangle, and you just fold it. So just the Z2 fold on this guy gives rise to a new set of mesh relations, and that gives you a different polytope. That's a polytope for CN. The polytope for DN looks like a mesh, wave equation mesh, almost everywhere, except there's something a little funny at the bottom. There's a doubling of the variables on the two sides that corresponds to the presence of the anyway, I don't have time to explain it in any more detail right now, but these are very simple mesh pictures, and from the meshes, just like we saw before, you very directly see how causality in the mesh enforces exactly the kind of factorization properties that we expect. In the particular case of Dn, that corresponds to one loop phi cubed integrands. There's a little bit more interesting things that we can say, because Dn actually naturally doubles the kinds of propagators that you can have, but it also is a natural Z2 symmetry. So you can take Dn and actually slice it in half and get something that we call Dn bar. And this Dn bar now doesn't double any propagators. Everything is sort of nice and normal. And here's an example of what Dn bar looks like, decorating some of the vertices with the actual diagrams, just like the decoration of the icosahedron that we had before with the diagrams of the phi cube theory. All right, now, so that's what you can get just by playing with meshes. You've never heard of cluster algebra, you haven't heard of anything fancy, you're just playing around, you've noticed that 1+1 dimensions is cool, you're playing around and you want to find these kind of wave equation-like pictures that realize factorization, and you quickly discover things that give you that give you tree, tadpole emission, and one loop. But in fact, you can abstract away the rules, And this takes maybe a little imagination, but you can abstract away the rules by thinking about taking a walk through space-time. So imagine this is your space-time picture now on a grid, and this set of observers on this line, they're all compatible with each other. All the x's could be put to 0 at the same time. And now you can ask, how can I move that entire trajectory over to a new trajectory that has the same compatibility properties? So I want to find a set of observers that can sort of compatibly go and sweep through the entire space-time. Well, you see, if you're going to do it, you'd first have to move this guy over there, and after you did it, you can move that guy over there, then you can start doing other things as you go along. But you can abstract away this rule in the following way. First, you take all the dots and you draw them. Depending on whether the line from one dot to another goes in the U or the V direction, you represent that with an arrow going in or out. All right, so now we have a quiver that's associated with the picture of a particular sort of observer trajectory in this space-time. And then the rule for how you walk through the space-time is very simple. You can only, you have to find some node from which all the arrows are outgoing, and then if you find that, you switch them to be all ingoing. See, that simple rule of mutation on a quiver is encoding the proper walkthrough of this set of observer trajectories in the space-time. All right, and once you do that, you can also write down an analog of the ABHY formula, an analog of the Gauss's law mesh relation, which says that you associate a new variable with the vertex that you mutated, x prime, which satisfies x prime plus x as the sum of all the x's plus a constant. Okay, and if you do that, then there's a beautiful story here, but first, you can take any quiver and you mutate it to a new quiver. All you do is switch the directions of the arrows. You don't change the shape of the quiver. If you start with a tree-like quiver, the new x variables are some matrix that depends on where you mutate it times the old x variables. And the remarkable thing is that exactly this ABHY condition gives you a representation of the Coxeter group associated with the quiver. Okay? If you've never heard of Coxeter groups, you've discovered them like this. And you can then ask, if you want this polytope to close up and actually be finite, what does it take? Well, the Coxeter group has got to be finite. When are Coxeter groups finite? Only when the Dynkin diagrams, only when the quivers are Dynkin. So you discover Dynkin diagrams as an answer to this question. And in fact, the polytopes that you make in this way are exactly the ABHY realization of all the finite cluster algebra polytopes, a la what I just told you Hugh Thomas and his students realized, sort of inverting this logic to some extent after our paper. But if you've never heard of these things, this is a very natural way, just asking these questions, you'd be led into doing them. All right, so finally, a little note for later. All the polytopes that we just talked about are naturally given as a Minkowski sum of pieces, C1, P1 plus dot dot plus CM, PM, where each one of these PIs is the polytope given by setting a mesh constant other than CI to 0 and setting that of CI to 1. So here's an example seeing how you build a pentagon as a Minkowski sum of a triangle and two intervals. All right, so a summary of this part of the story is that 1 plus 1 dimensional causal meshes give us a simple origin for amplitahedra of phi cube biadjoint theory as ABHY realizations of ABCD cluster polytopes, a la Thomas et al. There are hidden symmetries exposed by geometry lead to new recursion relations through one loop, even for dumb old phi cube theory. And obvious question, what the heck is this 1 plus 1 dimensional structure? I don't know. It's kind of interesting that yet another two-dimensional structure is showing up related to amplitudes. It doesn't look at the worldsheet in any obvious way. It's very Lorentzian, right? Could this be some kind of Lorentzian worldsheet in disguise? I have no idea, but it's a fascinating and obvious question. All right, and so this is where we're at. For all the ABCD types, there are polytopes associated with them. All of the classical ones that have an N that could be related to amplitudes are related to amplitudes. The exceptional ones, we don't know how they're related to amplitudes. Meanwhile, we can go to higher loops, and it's clear that the higher loops are somehow also related to cluster algebras, but they're now related to the infinite type ones. I'll say something about that in a second. Another comment, all these cluster polytopes and the corresponding quote-unquote amplitudes or canonical forms, they'll have factorization on their facets and poles that corresponds to just removing a node of the quiver. So if I do it for AN, I remove a node, it factorizes into 2. I can do it for E6 and remove a quiver, and it factorizes into 3. That's not something we normally ascribe to particles in space-time, but there's a very well-defined factorization property, which is inherited by the amplitudes, the polytopes, and as we'll see, by stringy generalizations of all of these things in a moment. Let me just make a 30-second comment about what we know at all loop order. So there's an obvious reason why one loop is related to cluster algebras associated with surfaces with one puncture on the inside where the corresponding in a dual diagram to the loop integration variable. The problem is, as we go to higher loops, the loops interact with each other, and when they interact with each other, from the clustering point of view, as you do mutations, there's a variable you need to keep track of that we don't care about in amplitudes, that corresponds to the number of times as you go from something on the outside to one of the internal loop points, you wind around one thing before you end up on the other. This is a totally dumb infinity that we do not care about in amplitudes, and yet it's sitting there in the cluster algebra world. And so here's what we know, and this is work in progress with Hadley Frost and with Giulio, which is that if we take the d log of all the x's associated with all the diagrams, and now we ask, can we build a projective form, which means that we have to start with one diagram, mutate, and see if it's possible to consistently assign signs in such a way that when we're finally done, all the projective variation of everything cancels and we're left with things that are projectively invariant. This is highly non-trivial. This is possible even for the normal finite type cases. This is highly non-trivial, just the way I've set up the problem, that such a thing is possible. It's definitely not obvious when it's infinite. You might not even think you get something finite by the time you're done. But here's all we do. We do this process with mutation, then we deal with this infinity in the dumbest way by just identifying all the variables that only differ by these stupid winding numbers. And the magic is that we still get a finite, projectively invariant form. Okay, this is quite remarkable. And so it means that this hidden symmetry of phi cubed by adjoint survives to all loop order. What we don't yet know is what the geometry is that's supposed to go along with this, what the polytope is that's supposed to go along with it. But there's clearly something there, and this hidden symmetry is there to all loop order. All right, now let me switch to the second topic, stringy canonical forms. This is work in progress with Song and with my friend, the mathematician Thomas Lamb. So, a quick review of something that Thomas and Jan Taubay and I talked about a couple years ago, Newton polytopes and the push-forward map. So let's say you have a polynomial in some number of variables. We can write it in this compressed notation. This is sum over some integer vectors AV, x to the v. And the Newton polytope associated with this polynomial is simply the convex hull of all these integer vectors v. Here's an example. So what we talked about a few years ago is that there's a very simple way of mapping like a simplex, a very simple positive geometry, into a complicated one, when it's a polytope anyway, by this Newton polytope map. So if you have a polytope, here's a polygon that I'm trying to map to with sort of random vertices, all I have to do is start with an integer representation of it, and then take the integer vectors associated with that, and then map from this little x space into the y space of this polygon by this simple map. And that maps the inside of this triangle beautifully one-to-one into the inside of the polygon. And if I take the canonical form for this little simplex, and I push it forward and sum over all solutions, like you're used to doing with scattering equations in CHY, then that gives me the canonical form of the polytope. So that we've known for a long time. The new thing is this very simple definition of a stringy canonical form. So let's say I take the simple canonical form of a simplex and I just try to integrate it. Why not? Well, why not is if I try to integrate it from 0 to infinity, I get infinity because it's logarithmically divergent. So let me try to regulate it by taking a product of all of these little x's to some positive powers, x capital Xi, with some parameter alpha prime. That takes care of the divergences near x equals 0. There's still divergences near infinity, so I'm going to put some big polynomial p of x to a negative power to hopefully take care of that. Okay, so now this is potentially a convergent integral. And then I can make a form out of it just by wedging this guy with all the d capital X's. All right, now here are the claims. The claim is that this integral is convergent if and only if the Newton polytope associated with this polynomial that I'm using to tame infinity is top dimensional, And if this x, if all these x's lie inside C times this, lies inside this polytope. Okay, so that's just the condition for convergence of the integral. But furthermore, if I send alpha prime to 0, having put the alpha prime to the n out in front, this omega alpha prime actually turns into the canonical form, the standard canonical form of that polytope, C times P. But for general alpha prime, it's a beautiful meromorphic function. It has infinitely many poles. And it has the same properties a canonical form does, that it factorizes on itself when it goes to boundaries. So this is a natural generalization of the notion of canonical form that now is meromorphic, like string amplitudes are, except it's true for any old polytope. Well, any polytope that I can realize with rational vertices, which is, some cannot be, some very weird ones cannot be, but many can. All right, so now, given this thing, we can now ask, there's a simple connection between the push forward and scattering equations / CHY. If I start with Gross-Mende, I can ask the analog of Gross-Mende, what are the critical points of this equation when alpha prime is infinity? And it's a trivial calculation. See, the critical points of this equation are precisely the Newton polytope map from the little x space into this big polytope in capital X space. So, by the previous argument with Yuntao and Thomas, we know that the push forward then gives us the canonical form for this polytope, which is exactly alpha prime goes to the limit of I. So this gives a sort of one-line conceptual understanding for why the Gross-Mende limit and the low energy limit are the same. And has nothing to do with strings. It's true for totally random polytopes, and it's a feature of any old canonical, of these stringy canonical forms. There are trivial generalizations. If you have many polytopes, if you have many polynomials, then you get exactly the same thing, except the polytope that you get is the Minkowski sum of all these pieces. There's a closed string generalization as well, I won't talk about, but once again, as alpha prime goes to 0, we get a canonical form, pushed forward via scattering equations, quote unquote, generalized scattering equations. For general alpha prime, it self-factorizes. This is a totally general phenomenon. Now, we can apply this to a much more special example where something much, where more magical things happen. We can use this to define string amplitudes associated with all these cluster polytopes. For example, if I take AN realized as ABHY, the association realized as ABHY, remember, it was naturally given as a Minkowski sum of pieces. So if I take those pieces and I shove them into this integral, to define a stringy canonical form. I've never heard of anything. I'm just sort of playing with these stringy canonical forms as intrinsic definitions of canonical forms for polytopes. I get the Kobe-Nielsen string integral. This is something that I mentioned at the last amplitudes I really wanted to see, but which we had not seen. Some intrinsic in kinematic space definition for what string amplitudes are, making no reference to the worldsheet or CFD correlators or anything like that. Well, here it is. Okay, so we see strings from combinatorial geometry in the kinematic space with no standard worldsheet. But now we can do it for general ABHY realized cluster polytopes. There's a stringy canonical form, which are string amplitudes for all cluster algebras. And the string magic generalizes. It's there for all of them. They're all meromorphic. Remarkably, they all factorize on massless poles, even at finite alpha prime. They have things like ST channel duality in their general, and their all n generalization, exponentially soft in the UV. Now we know that BCD types also, as alpha prime goes to 0, give us physical amplitudes. They give us one loop amplitudes for the biadjoint theories. So what is the physical interpretation of these suckers at finite alpha prime? We don't know. More in general, these stringly canonical forms define various compactifications of interesting spaces. Just to give you an example, I can take a random cluster algebra, finite, infinite, doesn't matter, okay? Random cluster algebra, and I can pick one cluster, take the standard D-log form associated with one cluster, and then decide that I'm going to build these stringy canonical forms with any set of A variables of this cluster algebra I like to powers. If I had a finite cluster algebra, I could do all of them. In general, I could pick some subset of them if I like. I don't have to choose all of them. They all give me interesting integrals. And if I choose fewer of them, I'm getting blowdowns of the polytopes I get from more complicated ones. So a particular example here is if I choose what we'll later call GKN mod T, where if I do this for GKN, and instead of taking all the cluster variables of GKN, I can just take the minors of GKN. That gives me a beautiful set of stringy canonical forms where I take the usual canonical form on the positive Grassmannian and I just weight with the product of all minors raised to powers. These are also similar to integrals that Freddie and friends have been talking about recently. Okay, and these things are different. it's trivial to figure out, not totally trivial, but it's conceptually trivial to figure out what they look like simply by taking the Minkowski sum of all the different pieces. And just so you see, there are interesting differences between the full cluster case and the GKN mod T cases. In the cases where the clusters are Grassmannian, these are the facet counts for the polytopes in these cases. And if you look, indeed, the ones here where there are fewer variables occurring with only minors and all A variables are smaller. As you go further down, they have fewer facets than the ones upstairs do. So these correspond to somehow different compactifications of what you might think of as the interior of positive GKN modulo the action of the little group. All right, so the summary for this part is that there is a stringy canonical form for any rationally realizable polytope P. It's simple conceptual understanding of CHY and scattering equation push forward map for any polytope, which is nothing, this has nothing to do with strings per se. This is a totally general phenomenon. It's especially nice in the case of string amplitudes for all finite type cluster algebras. I can't really explain in detail what the especially nice means here, but and finally, there is something special about the usual scattering equations, which I find very amusing, that if I took a random realization of an isosahedron in this picture and I asked how many solutions would contribute to computing the form, I would get a number that's enormous compared to n minus 3 factorial. This is actually hysterical, because I always thought n minus 3 factorial was a huge number. In fact, n minus 3 factorial is a tiny number. It's the smallest possible number of solutions you can have contribute. And there is something special about these, cases. All right, so I think I have zero time, but let me just say a few things, especially since if I screw up, I'm running away afterwards anyway, so all right. So I said a tiny bit about this at amplitudes last year, and Song will talk about it more at strings next week. So this will be done a little bit more detail, but let me say something quickly. If we think about these geometric realizations of a combinatorics, polytopes are still a little floppy in the sense that if I want to sort of say that I'm drawing a shape that's telling me that this edge is far away from that one, it's true that when I realize it as a polytope, these faces don't touch that one. But the linear equations that cut out these faces certainly vary as I move along this one. Can we do something even sharper than that, something more binary? And so here's the thought equation I already talked about last year. Can it somehow be possible that we associate with every facet of some geometry a variable u, and we write down an equation, a curvy, a nonlinear equation that looks like u plus the product of all the incompatible u's equals 1. And you see if the u's are positive, this also forces them to all be less than 1, and this equation would force that if one u goes to 0, all the incompatible one goes to 1. That's a sense in which it's binary. Now the amazing thing, this is so conjectural, the amazing thing is as far as we know, these equations literally as written with all the powers 1 there are only consistent for isosahedra, where this is the equation. There's a uij associated with every chord of a polygon, the equation is uij plus the product of all the KLs crossing ij equals 1. Right? Now you can generalize that equation by allowing general powers, and general cluster geometries have equations like this associated with them, where these numbers are called the compatibility degrees of cluster variables. And in fact, you can think of these u's as closely related to ordinary x cluster variables as x over 1 plus x for very special cluster variables, which are exactly the ones that we encountered, the ones where all the arrows are going out, what we encountered in all the walk to the clusters that we talked about before. The beautiful thing about these u's is that there are as many u's as there are a variables. They're multiplicatively independent. I think they're important objects. There's more to say here. Directly from these u equations, you actually discover more general form of these nonlinear equations, even for the case of an. And it's these equations that actually tell you that these u's are cross ratios, and tell you that the u's are actually a gauge invariant description of the world sheet. All of this generalizes to all Dinkins. And that also allows us to understand the notion of orderings. So when we have for an, we know we can think about endpoints on a disk. But the definition of the u's by themselves seem to pick an ordering. So how would you see all the other orderings if you only saw the definition of the u's themselves? Well, quite beautifully, these, if you just ask for all the possible sign patterns that the u's can have in this u plus u equals 1 equation, you discover for the normal an case, there's exactly n minus 1 factorial over 2 of them. And the equations have a beautiful action of a Sn symmetry on all of them. So in fact, the real U space, not just restricting to U between 0 and 1, sees all of the orderings. And all of this carries over to general finite type algebras. The U plus U equations, sign patterns, define other orderings. But unlike what we're used to with the open string world sheet, new shapes appear. For example, for B2 and C2, there's 16 orderings, of which 4 are hexagons and 12 are pentagons. For G2, there's 25 orderings. There's 1 octagon, 4 hexagons, and 20 pentagons. And we can also talk in this U language about exactly these generalized string amplitudes that we talked about before, where again you integrate over the cluster canonical form, but now the regulator is just taking all the U's to a positive powers. Now, there's also a natural origin and actually generalization of all these U's for totally generally stringy canonical forms. And they have a lot of the many properties in common, but the binary character really is special. And generically, you would find, for example, equations look like U plus UUU is almost equal to 1. It's equal to 1 in the sense that it's the ratio of 2 polynomials P and Q whose Newton polytopes are the same, but it's not literally equal to 1. For literally, the cluster cases, we get something literally equal to 1. Finally, let me say 2 minutes about GKN mod T and n equals 4 symbology. It's something I already talked about last year, is that the space determining n equals 4 integrand we know is the amplitahedron, and its most invariant way of talking about it that we know of so far is in momentum twistor space in this winding number picture, what I called last year GK m comma n. So there's a natural guess. What could be the space associated with the amplitude itself? Then we have to find a question to ask in that space. But first, what could the space itself be? Here the question is, what's the form of logarithmic singularities on the boundary of the space? Here we don't know what the question is, but we'd like to know what the space is. The natural guess was just exactly the space modulo the action of the little group, which is where cross ratios come from. Last year I was somehow under the impression that for k equals 0, for MHV, this was somehow all understood by people other than me. And so the interesting thing was for bigger k. That's why I talked about some funny things with weird tori and so on at MHV. But in fact, it's already mysterious for k equals 0. So, for example, supposedly G plus 4n mod T is just the cluster X variety of G plus 4n, but this sucker is infinite already for n equals a. However, we know that G4n itself is not infinite, so what the heck is going on? Let's remind ourselves how it works for G2n mod torus. Mod little group, where what we have is a famous bubbling picture for the boundary. So I have 5 points on the boundary of a disk, and on the boundaries, it bubbles into 2 pieces like this. Right? So one thing we'd like to know, now we go to higher k, we have configurations of points with various linear dependencies. What's the analog of this bubbling picture? What's a natural generalization of this? Now, here's the picture, just geometrically. Consider any point in the Grassmannian and look at its minors in this large space known as the Plücker embedding. Now, take a given point in the Grassmannian and rescale all the columns. Ci goes to Ti, Ci. And look at this entire orbit as Ti ranges from 0 to infinity. By very general Newton polytopology, the image of this thing up into this, in this big Plücker space projects to a beautiful polytope known as the hypersimplex. This is just all hypersimplex is. Consider an n-dimensional vector of zeros and ones with exactly k ones. The convex hull of all these guys is called the hypersimplex. Right? And that's the image of a generic point in the Grassmannian under the action of the torus. Now let's say you go in the Grassmannian and you approach the boundary. Right before you hit the boundary, the image of this orbit is the full hypersimplex. When you hit the boundary, it's going to break up into pieces because you're seeing different parts, different cells. So, but it can't break up into pieces in a random way. It has to break up into pieces in the following, made out of the following objects. Known as positoid polytopes. Take any cell of the positive Grassmannian upstairs where you're hitting. Only some minors are non-vanishing, so take all the 0, 1 vectors that have 1s in the columns of the non-vanishing minors. The convex hull of these is known as a positoid polytope, and that tells us what the boundary of at least this natural geometric notion of GKN mod T is. As I said, just before you hit the boundary of the torus orbit of the hypersimplex, when you hit the boundary, you should triangulate the hypersimplex into non-overlapping positoid polytopes. That's the generalization of the bubbling picture for any k and n. And so, for example, we could talk about what the boundaries of G36 mod torus look like, just geometrically. So The interior is just convex hexagons, but as you go to the boundary, the analog of bubbling turns out to be that 1 and 2 can collide with 3, 4, 5, 6 generic, or on the other side of the bubble of the other world is 1 and 2 are generic with 3, 4, 5, 6 on a line. Or like this. Or these are the new things that can happen that we're not used to, where 1, 2 on top of each other, then 3, 4, and 5 and 6 generic, plus it's 2 cyclic friends. So this is a 3-component boundary. We're normally used to just bubbling into 2 pieces. This is already an interesting 3-component boundary, and there's 2 kinds of these. Now, this is the totally geometric definition of GKN mod torus, and it's also what we get from the stringy canonical form that I've already mentioned, where the integral is given over the Grassmannian with the usual measure, modulo torus, and it's weighted with the product of all the minors to powers. Choose your favorite positive coordinates, do the Minkowski sum of the Newton polytopes, and you get the associated polytope. So this is an object that's manifestly finite, but it's big. G48 mod torus, for example, has 360 faces and 90,608 vertices. But it's finite. So that's great. This is mathematically very beautiful. Is this the right space for n equals 4 amplitudes? We don't know. We're still investigating. There's one peculiarity, which is that even though G48 is parity invariant by itself, G48 mod torus is subtly breaks parity. There's actually even smaller manifestly parity invariant compactifications of G4n mod torus that we could talk about. From the language of these integrals, we could go back and not put in all the minors, but only put in this interesting subset of minors that are manifestly close into each other under parity, and which are sort of motivated from the sign flip pattern picture that we talked about with Hugh Thomas and Yara a couple of years ago. And see, already you see again, there is an interesting difference for n equals 7. This object is smaller still. This is what you get from G47 mod torus. This is something you get, this is smaller in an interesting way. So clearly there are a number of ways of taming the infinity here, but which, if any, are right? We don't know yet. We don't know if any of them are right. It's a very interesting question to try to figure out how to cut out all the boundaries and match them with symbols that can, symbol entries and so on. But from my point of view, there's something very systematic that can be done that I'm hoping to start spending more time doing now that these other things are out of the way. Beyond guesswork and pattern recognition is that there's a rather miraculous thing from my point of view which has happened from people studying Landau equations, which so they always say that everything that you get out of planar Landau equations always gives you polynomials and the variables that are positive in the positive part. Well, inverting that means there's some deep reason that's completely unobvious why when the external data is positive, you never find solutions of Landau equations. I think this is a remarkable fact, and it deserves to be exposed and understood in a deep way. Okay, and it's probably some clue to what is going on here. All right, so let me now finally end. I said this is the big picture that I've been thinking about for 10 years, many people much longer than me. And the big picture issue still remains. We're still sort of playing around on the outskirts of a grand problem. Ultimately, what is the intrinsic, non-perturbative question in kinematic space to which the amplitudes are the answer? And I've been drawing this picture for years with all these incoming lines, and one thing I can say, at least roughly, is that we're also seeing many incoming lines of ideas that are starting to crash into the same basic territory. I find this personally fascinating. I did not expect these things would be so closely related to each other, that one set of questions about Grassmannians that you might care about for n equals 4ology are closely related to calculations you do with scattering equations in CHY and ABHY associahedra, and all this stuff are in the same intellectual soup. To me, this is fascinating. Something I've put in blue here is an object which is lurking around. None of you give a rat's ass about this other than maybe Yara and me, but I'm absolutely positive this guy's out there and is going to have something to say about this when before all is said and done. And of course, there's many other things going on, which I would love to couple into more, but there's just too many fascinating things going on. There's the recent definition of the amplituhedron in momentum space that you'll hear something about. These cousins and extensions of these ABHY cluster polytopes, Stokes polytopes, accordiahedra, and so on, that I don't know enough about, and many other things. The connection to integrability is a big one. What's going on the celestial sphere? Fishnets I find totally fascinating. So there's a huge number of ideas I think are starting to collide on on common territory. And let me just finish by saying that, again, for me, this is the 10th year I've been coming to the amplitudes meeting, sort of roughly 10 years since I've started thinking about the physics of scattering amplitudes. And I have to say, this community of people working on this subject is one of the coolest and most interesting and fascinating group of people that I've run into in my career. Every meeting that I've come to has been buzzing with some amazing idea by somebody, often more than one, and just really an amazing thanks to all of you, first of all, for inviting me to these meetings, letting me talk over time so much, and really, and more importantly, making it a really exhilarating journey so far and onwards to Amplitudes 2020. Thank you very much.
Okay, so, and thank to Nima for this wake-up call. So, are there any questions before he dashes out on a flying polytop?
Here's a question. So out of these 360 letters, let's say A coordinates or symbol letters, do you remember the maximal polynomial degree of them in Plucus?
I don't remember off the top of my head, no. And also, the thing is that we're trying to find the analog of U variables. We're trying to find the actual, you know, this is supposed to be GKN mod torus. And so there should be some proper, responsible torus invariant way of talking about it. There is a proper, responsible torus invariant way of talking about the other finite type ones. We would love to have a proper finite torus invariant. That's right. But anyway, but Mark, who has all this data and knows all about it more off the top of his head than I do, can tell you when I'm gone. Yeah.
Any questions?
So let me start with one more philosophical one. When you introduced the amplitohedron with your collaborators, one of the claims was that basic tenets of QFT like locality and unitarity are no longer hardwired, they are consequences. At least in the first part of your talk, you talked about causal diamonds. So it seems that causality, okay, perhaps in some
it's some very weird kind of causality. That's right. I don't know what kind of crazy causality it is. That's right. Yeah. Look, yes. So it's not causality in ordinary space-time.
Yes.
And yeah. So I don't know. Really, what's added in the first part of the talk is in the AVHY paper, we pulled these equations out of our asses. Okay. We said, here's very simple looking equations. They're very simple. They're very simple. So you write them, they're very simple, and then you observe that they work. And also to even observe that they work, you have to take certain linear combinations and sums of them and so on. The thing is that this wave equation picture just makes it obvious what's going on, right? That's, so it geometrizes all that chain of relationships and arguments and all that stuff. And in fact, it also told us things about the realization that we didn't know. This forgetting business was not obvious before, but it's totally obvious from the geometry. What that does that causality something deep? I have no idea. As I said, it's kind of weird, eerie, that we run into another 1 + 1 dimensional structure that does not appear to be the string worldsheet, but is associated an awful lot, like you take a bunch of things, you put points on them. I mean, it does not look terribly different than the way you do a calculation with a normal Euclidean worldsheet. But of course, you're asking a totally different question of this 1 + 1 dimensional space. So I have no idea if it's coincidental or if it's deep. But part of the reason I'm excited about these generalized stringy amplitudes associated with these cluster guys is that they give us a zoo of objects which sort of at least whether or not they end up being directly related to amplitudes at finite alpha prime. At alpha prime goes to 0, some of them are at least definitely related to amplitudes. Whether or not they end up being related at finite alpha prime, there is something which does stringy magic without looking like strings. And so I would really like to understand that, because for decades I was told, look, this thing about ST channel duality, only strings do that. My God, this picture of the tubes this way, that way. Okay, we have all those things with none of those pictures. So what's going on?
And in relation also to this zoo, sorry, for the 7 particle amplitude in equals 4, so in the last part of your talk, this blowdown of the cluster polytope, this GR plus 3,7 and so on, you showed that it has, for example, 392 codimension two phases.
Yes, yes.
Perhaps Mark has already let you know, but
Yes.
This can only fit the MHV amplitude. The NMHV heptagon seems to be larger than this, at least at this stage.
Well, so you see, from my stage of ignorance of last year, as I said, I somehow thought only I was dumb and I didn't know about k equals 0. MHV was sort of one way or another style. That shows how little I knew. That's why last year when I talked, I was talking about k equals 1, and there's something new for k equals 1. It's not just positivity, it's this business about winding as well. And then there's a lot more to worry about with the R invariance out in front, and anyway, there's a lot more to worry about for a higher k. This is literally for k equals 0. What it has to say about other problems, I don't know, but yeah.
Thanks.
Okay. James.
Just a quick question about alpha prime for strings. So real strings is not just massless modes with an alpha prime expansion. It's got all these massive states and all sorts of stuff.
Yes.
So
no idea.
Is there any analog?
At the moment, no idea. Well, all we know. So it's as if you could imagine trying to go back and pretend that you were the people in 1967 or whatever, right? Take these massless formulas, take the Kobe-Nielsen form, a general N, and try to factorize it and discover oscillators and all that. We have not played with that much yet. But as you know very well, if someone just handed you the massless amplitudes and nothing else, you would discover they factorize on the massless poles. It's already a miracle they factorize on the massless poles, right? I mean, the fact they factorize on the massless poles tells you there's a consistent low-energy effective field theory that goes along with them. Of course, they further have to factorize on massive poles, but then you have to know what the heck you're scattering in the massive states, and that's a wonderful question, but we don't have any picture yet for what what the massive amplitudes might be.
You can see these poles, something like the
Yes,
poles.
yes, definitely. They're meromorphic functions. They have infinitely many poles. It's qualitatively exactly like string amplitudes.
Let's thank Nima.
Thank you.